it is divided by the probability of event B here. So the interpretations of this one would be that we already know the event B happens, and now we are kind of interested in what is the probability if A happens as well. Okay, so that's why we are looking at the intersection of event A and event B instead of just event A itself. Okay, right. So here is an example using the table 1. Says that now this is kind of a mean question. So it's like you goes out and I tell you like this person has the college degree. Then what is the probability of that person has a higher wage there? So based on that table, then we can do this kind of calculations. Yeah. Right. And again, by using the graph, it looks like this one. Okay, so this is the sample space. We have event A and event B here. Okay, and now we want to see, or we want to ask what is the probability of event A given that event B already happens. So one way is to interpret that in that way. The other way is that, okay, so this is the original sample space. And we kind of like focus or limited our attentions to the event B here, because now we already know that event B happens, right? So we limited our attentions only on this part. Okay, so this part, okay? And we want to know what is the probability of event A happens as well. And the only possibility is that for event A to happen is this area, right? Because this is the intersections when A and B happens at the same time. Okay, so it's kind of, we limited ourselves to look at this one, this part of the sample space. Right? Okay. And then independence. Okay, so when we code event A and event B are statistically independent, then that means the probability of the intersection of these two events is actually the multiplications of these two probabilities. Okay. And again, so if we have that, then this will directly become if these two are statistically independent. Okay, we use this symbols here. Where is it? Where is it? Here. To show these two events are independent. Okay. And once again, to think about that concept graphically. So what does that mean? It means the proportion of A, so the event A has a certain proportions of the whole sample space. And that proportion, or that ratios, actually equals to this intersections, the ratio of these intersections over the event B, right? So it's proportionally decreased when we only look at the B event, right? So that is statistically independent of these two events. Right, so I will show you the first bullet point here, and you can do it by yourself for the second one. Okay, so remember that we have the first theorem, which is the partitioning theorem here. Says that every event can be written as the union of all the intersections between the event A and the partitions of a sample space. Okay, and here we kind of related it to it. Okay. Use this one. Okay, so from the theorem 1, and according to this graph here, so the event A is actually the intersections of the union of the intersections of event A and each part of the partitions from B1 to B4. Okay, and since we know that is actually a partition means that each of them are not intersect with each others. So the probability of event A is actually the probability of each part of it. You just add it up. So you can put a sigma here, and then you do a little bit manipulations here. You tied the probability of B I and divide it by probability bi as well, which does not change the result, right? So you can write it this way, and this is exactly the left-hand side here, the first term here is exactly the expressions of conditional probability, and that's why we can get these terms there. Okay. Okay, then is the best rule here. So from my personal experience, I don't quite understand this rule, to be honest. But let me tell you like how people use it. So one way is kind of like I don't know the probability here, but somehow I know the probability of the other stuff. So I can use it to kind of compute the probability I want here. Okay.